Hi everyone, this is Jesse here from SkyCiv, and today we're going to be looking at example 3.11 from the Australian Guidebook for Structural Engineers, which is an example of an Australian Weld Group Capacity Calculation. Now for this calculation, I'm going to be using the Quick Design Weld Group Capacity Calculator, which I have open now, and you can find by looking in the Quick Design library and searching for Weld in the Australian section. With this tool open, we can specify the leg length of the weld as we'll specify 8 millimeters, but this problem is kind of about finding this length that we need. We can see that generally in calculations we'd use the throat thickness. Here we can see that value is 5.66 millimeters, and that's just from trigonometry. It's the length of the leg divided by the square root of 2. And we have other properties, the thickness of members, which isn't given in this problem. It's not a check required in this design problem. But for the Australian standards, is something we can take a look at. And we'll for now consider that we have a 490 MPa weld strength and it's SP weld. So we close this off. For adding in our welds, so in our graphics here, we can see, I'm just going to remove everything, this dashed line which represents the column which we are potentially about to add. So these are the possible welds we might add. For this design problem, we've been told that we have an I section with a width of 305 millimeters and a height of 293 millimeters. The closest section to this is a 310 UC 96.8, which has the width of 305, but is slightly higher than the problem has specified. So we can just use this to get a rough value. And for welds, we're going to have welds on both sides. So if I put outer side only, we can see where those welds would go. Inner side only, we can see where those welds would go, but we want to be fully welding this section. And we can now apply the welds. So now we can see these welds have been secured in the model, and these will be used when we do our calculations. And for our design loads, I've already pre-input these to be able to design problem specified. So these are factored loads that we use in our calculations. Now we can press run and we can compare this to the design examples. Here on the right, we see a summary of our geometric properties, the critical stress point in our weld group, the resultant forces on our weld group, and the utilization for our weld group. So we can see in the report how all these calculations take place to get those values on the right. The first thing we do is calculate the centroid for our weld group. This is not done in the textbook example because they've used analytical calculation, like a predetermined calculation for an I section. This is a very general approach. So if we deleted any one weld, we'd still be able to do the calculation. Whereas in the textbook example, if we deleted any one weld, it would get extremely confusing straight away. They've used a fixed formula, which doesn't allow for this kind of customization. So here we can see these are the properties for each weld. Each row is a different weld. We can see the X, Y coordinates, the length of that weld, the centroid of that weld, and the length times the centroid for that weld, which we can use these two columns at the end to get the actual centroid. Then we have our second moment of area calculations. Again, it's in a table form, and we can see these results here with that we get IX as 29.35 times 10 to the power of 6, and 9.47 times 10 to the power of 6 for IY. Finally, we can add these two together to get the polar moment. And these values as compared to the textbook, in the textbook it's 30.3 times 10 to the power of 6 and 9.457 times 10 to the power of 6, with a final polar moment of 39.8. So it's very similar, but the difference is just coming from because they've used a slightly different section, which I can't find the real world version of that section. So we have the summary of our weld group properties here. And then finally, we can do our calculation for that weld group to find the stresses at the most critical point. So in the background, there's a calculation to check where is the most critical point. And then we show the calculations of the stresses for that critical point. And this uses the geometric properties of the weld, the polar moment, the length of the weld, for example. And using these geometric properties, we're able to resolve forces on the weld, like moments, into pure shear forces. In this calculation, the final step is combining the shear forces in each axial direction into a resultant shear force. And here we get very similar results again. We get this final value of 1.18 kilonewtons per millimeter of shear force. In the textbook, it is 0.082 squared plus 0.099 squared plus 1.138 squared. And that gives a final result of 1.15 kilonewtons per meter. So it's very similar. And finally, we can see that the utilization for the weld that we've specified, an 8mm SP490 weld, passes. So that was the entire calculation, and we can see it was very easy to input all those properties. If we wanted to change the inputs to be the exact same as the textbook, we can do that. So we could, for instance, go to the graphics, just so we can see everything quite easily. We can remove all these welds, and we can just input the welds as have been specified in the textbook. So we've got two 305mm long horizontal welds, one at 0. But the thing in this calculation is that there is a weld on the top and the bottom of the flange, but in the calculation they're kind of assuming they're at the exact same position. So I'm just going to duplicate that row to have two of the same. And then we have that same weld at a height of 293mm, and again there's two welds in theory at the exact same position. And for the vertical weld, that's at the halfway point, which is 152.5, going from 0 to 293. And again, we have a duplication for that weld. So I'm going to save that. We can run that. And now we can see that we'll get a warning because we do have the overlapping welds, so it's not obvious in the drawing. But in this case, we're allowing that calculation to run because you might want to simplify, just like the textbook did, to do that kind of calculation, that kind of simplification. So here we have these final results, which are now the exact same as the textbook. So these are the exact same values that I said before, just some rounding differences, and we get quite similar utilization to if we just assumed it was a realistic real-world section of a 310 UC 96.8. So that's been design example 3.11 of the Australian Guidebook for Structural Engineers. Thank you for watching this video. If you have any questions, you can leave a message here for me and the team, and we'll get back to you as soon as possible.